Hi, in this video lesson we're going to be talking about orbital motion. Keep in mind that we're just going to skim the surface. I've cut out all the math and we're going to try to keep things really simple. Before we can talk about orbital motion, we have to talk about the idea of parallax. Parallax is a way of estimating the distance of an object given the apparent angles that we observe. So you probably experienced the idea that if you're moving and you look at something closer to you, what's behind it will change. Um, and the angle at which it changes can give us a clue as to how far the thing is that you're looking at. So close objects change against their background a lot more than far objects do. So once again, parallax is the apparent change in position of objects with the changing position of the observer. The best way to look at this is through a picture or through a little model you can do in class. So if we look at these two people looking at this tree in front of the mountain, each person, given their position, sees a different mountain peak behind the tree. However, if that tree was much further back, closer to the mountain, there's a pretty good chance that both of them would see this peak between them because of the different distance. When we look at stars, or what a guy by the name of Tycho Brahe did with planets, is that we can look and see what object or what stars appear behind an object in space. And that can give us an idea of how much the background changes, can give us an idea of what the distance in the planet is. So an object that is very close, in the case of Tycho Brahe, he was looking at a supernova that had occurred, and people thought it was very close because they thought space didn't change. And so he looked at that supernova, and he if it were close, as people thought, he expected that the stars or the constellations that appeared behind the supernova should change a lot. In actuality, the supernova was fixed among the stars, indicating that it was much further away. Brahe used the idea of parallax to gather a lot of data about the distances in space. So one of the things that he concluded from his data is that the universe changes. As I mentioned, there was a supernova, and he showed that supernova was in space as opposed to in Earth's atmosphere, indicating that the universe can in fact change. He also, and most importantly probably, took very detailed observations about the motions and the distances of the stars and the planets. And so he was able to give really good records of how far each planet was given the parallax that he calculated. As part of that, he showed that comets were close like planets were, as opposed to far like stars. He also made a number of new instruments for observations, and all of the data that he collected about the distances to planets was passed on to his apprentice, or in other words, his employee, Kepler, who worked after him and came up with a lot of really important conclusions about orbital motion. Let's take a minute and review parallax. So Brahe's data was passed on to Johann Kepler. Johannes Kepler was a mathematician whose goal it was to figure out the layout of the solar system. And he knew that it had to fit the data collected by Tycho Brahe, and it had to fit the observations and conclusions made by Copernicus. When all was said and done, he came up with 3 laws that basically govern how objects orbit. Now I'm going to kind of throw a monkey wrench in our little story of how we figured everything out, because as we go through Kepler's laws, I'm also going to talk about Isaac Newton. Isaac Newton lived long after Kepler. Newton wasn't even born when Kepler died, but his laws explain why Kepler's laws work. So as we go through Kepler, we'll also talk about Newton. Before we move on, we should talk about why planets orbit at all. To find that answer, we have to look to Isaac Newton. You've probably heard that Isaac Newton developed several laws of motion. Those laws govern anything that's moving, not just orbiting objects. But in developing those laws, we can understand why objects orbit. So Newton's first law is the law of inertia. Basically, the law of inertia says that an object that's moving is going to stay moving in the same way. In other words, it won't change direction and it won't change its speed unless there's a force to cause those changes. So, according to Newton's first law, a planet that was moving, just because all things are in the space started off moving after the Big Bang, and so a planet that's moving as it formed and as it's collecting stuff should be moving in a straight line. Planets don't move in a straight line, though. They curve and orbit the sun. So consequently, there has to be a force changing it from going in a straight line and causing it to change direction. And that force is gravity. That leads us to another one of Newton's laws. It's not one of his laws of motion, but he did develop it, and that's the idea of universal gravity. So his law of universal gravity describes the force that pulls all objects together. When we talk about gravity, there are two factors that affect the force of gravity: mass and distance. Mass increases the force of gravity, so larger objects have a larger force of gravity. Distance decreases the force of gravity, so closer objects have more gravity. If we compare which of those two factors is more important, mathematically we'll find out that it's distance that's more important. That's why the moon causes tides, even though Jupiter, which is much larger, doesn't. Jupiter does affect us, but it's nowhere near the effect that the moon has because the moon's so much closer. Let's take a minute and review why planets orbit. So, Kepler's first law was that the orbit of a planet about the sun is an ellipse with the sun at one focus. In other words, the shape of orbits is elliptical rather than circular, which was thought of at the time. So first, let's talk a little bit more about an ellipse. An ellipse is kind of like a flattened circle. In lab, we're going to draw an ellipse and come up with a more precise definition than a flattened circle. But basically, if you imagine a string, you can put a string on two thumbtacks and pull it taut, as this little animation is showing, and it will create this flattened circle. There's some mathematical relationships that exist as well. So a focus, or plural foci, is the point at which the thumbtacks were pinned. And of course, it's not a very precise definition. We're going to develop one in lab, so I'm not going to mention it here. Within an ellipse, there are two major components that we should label that we care about for now. One is the major axis, and that's the distance across. It's equivalent to saying the diameter of a circle, only we're talking about an ellipse. The semi-major axis is very much like the radius. It's the halfway point. In other words, it's half of the major axis. And the reason why it's important, usually we care a lot because it's the math. It's involved heavily in the math that we would do with this. The reason why we still care about it, even though we're not doing the math, is that it's considered the average distance to a planet. So we've talked about how the Earth's average distance to the sun is 1 AU. That means that the Earth's semi-major axis is 1 AU. Now, when we look at this, the semi-major axis, which is a halfway point, isn't always the distance. Sometimes the Earth is closer to the sun, like here, and other times the Earth is much further away, as it would be over here. So the semi-major axis is an average of all those distances, which comes out to be the same as half of the distance of the major axis. In your notes, you have a diagram. Don't worry about the minor axis. We don't particularly care about that. But do label the two foci. Notice you'll have to draw in the other one because at the other focus, there's nothing there. It's just a point in space. But label the sun as one of the foci, label another focus at the other side. The distances should be about the same. And then label the major axis, which is all the way across. And label the semi-major axis, which is half of that. In this diagram, they did it below because it would kind of get a little confusing. Let's take a minute and review general ellipses. Another characteristic of ellipses that we have to talk about is the eccentricity. The official definition for eccentricity is the ratio of the distances between the foci and the length of the major axis. That's a mathematical relationship that basically describes how circular or how flat the ellipse shape is. So if the ellipse is very, very close to being a circle, or could even be a circle, then the eccentricity is going to be a much smaller number than if it's wide out. So the equation is the distance between the foci divided by the major axis. That's going to give you a fraction, so your eccentricity is always going to be less than 1. If it's a circle, the distance between the foci will be 0. And so no matter what the length of the major axis is, 0 divided by a number is always going to be 0. So a perfect circle has the eccentricity of 0. A straight line, conversely, the foci are all the way at the end of the major axis, and so consequently it's going to be a number divided by itself, which is 1. So all of the eccentricities will fall between 0 and 1. Decimals close to 0 will be very circular, and decimals that are closer to 1, say 0.8 or 0.9, will be very, very elongated. As we take a look at these values, eccentricity of 0 is a perfect circle. As our numbers go up, our ellipse becomes flatter and flatter and flatter. Let's take a moment and review eccentricity. There's just a little bit more on the definition of ellipses we have to talk about. And you probably heard about it. It comes up on the news every now and then. And that is the term perihelion and aphelion, or perigee and apogee. Perigee and apogee, or perihelion and aphelion, describe the point in the orbit in which the planet is closest and the point in the orbit in which the planet or the thing orbiting is farthest away. So a lot of times you'll hear that the moon is at perigee. What that means is the moon's going to look a little bigger that night because it's a little closer, as opposed to when an object is at apogee, it's going to look a little smaller because it's going to be a little further away. Most objects have an eccentricity that's pretty small, and so it's not necessarily going to be hugely noticeable, the size difference between perihelion and aphelion, but there certainly will be a difference, and it will be accentuated when the eccentricity is greater. Take a moment on your diagram and label the perihelion position and the aphelion position. Let's review perihelion and aphelion. Let's talk about why Kepler's first law occurs. Why do planets orbit in the shape of an ellipse? Well, to talk about that, we have to talk about Newton's third law, his law of equal and opposite reactions. In other words, for every action, there's an equal and opposite reaction. Another way of saying that is forces occur in equal and opposite pairs. So, if the sun pulls on the Earth is pulling on the sun. And if Jupiter is pulling on Earth is pulling on Jupiter. Those pairs of interactions tells us that there's a lot of gravitational forces pulling and tugging at planets that are moving. And so when those pulls and tugs affect our orbit, what they ended up doing is kind of squeezing the orbit. So rather than being a perfect circle, the pull of the sun's of Earth's pull on the sun and sun's pull on Earth and all the other planets squeezes that shape into an ellipse. There's also some other factors that come into play, such as the speed of the planets and their mass, but for now we'll just leave it at the interactions of different gravitational pulls squeezing the orbit. Let's take a minute and review why planets orbit in the shape of ellipses. Finally, Kepler's second law is that when planets orbit, they speed up and slow down in their orbit. His official language was a line joining the planet and the sun sweeps out equal areas in equal intervals of time. So in other words, if a planet moves along the outer surface here, and these three shaded almost triangles are the same area, then it will take the planet the same amount of time to move from P1 to move to P2, as it does to move from P3 to P4, and to move from P5 to P6. In other words, this and this and this will all occur in the same amount of time. And so if the amount of time is the same and the planet is covering a greater distance, then it's going to be moving faster. So if we talk about speed that you would drive in your car, if you travel 60 miles in 1 hour, you're moving a lot faster than if you travel 10 miles in 1 hour. And so this is like moving a greater distance in the same given amount of time. So another way of describing his second law is that planets move faster when they're closer to the thing that they're orbiting. Consequently, the planet is moving at its absolute fastest when it's at its perihelion position and its absolute slowest at its aphelion position. So once again, it's going to move faster from C to D than it is from A to B, but both of those will occur in the same amount of time. Let's take a moment and review Kepler's second law. So why is it that planets speed up and slow down? Well, once again, the answer comes from Newton. Newton's second law specifically tells us that why, and his second law is that force equals mass times acceleration. Keep in mind that acceleration just means changing speed or direction. So, mass is constant. Planets don't lose and gain mass willy-nilly. They're pretty well fixed on that. And so, if mass is constant and the planet is speeding up, that means that the force of gravity is changing. Well, that makes sense. Because when the planet is farther from the sun, its force of gravity goes down because of the distance. If its force of gravity goes down, then the acceleration has to go down. It's going to slow down. If the planet is closer, then the force of gravity will be greater because of the distance, and the planet's going to have to speed up. Let's take a minute and review. Another reason why planets change their speed has to do with an idea of angular momentum. Angular momentum is the tendency of an object to keep spinning, or in our case, orbiting. Now this gets a little complicated, but we're going to keep it simple. So angular momentum, in other words, let's call it a desire, even though it's not alive. The desire to keep spinning is affected by three things. and it stays constant. So if one thing changes, something else has to change in order to keep it constant. Mass never changes, so that means that speed and the distance the mass spread out on are going to change in order to keep the amount of angular momentum constant. So, as an object gets further away, the distance from which its mass is spread out, in other words, there's mass in the sun, mass in the planet, and when we talk about the mass being spread out, we care about how far apart is all of the mass involved in this scenario. And so when two objects are farther apart, the mass is more spread out than when two objects are closer together. And so when they're farther apart, the speed is going to have to slow down in order to make the same amount of angular momentum. If two objects are closer together, the speed is going to speed up in order to have the same amount of angular momentum. And the best example of this is a figure skater. Most of you have probably seen a figure skating routine, and they almost all end with the figure skating doing a fancy spin, and usually they start their arms are flying around and their legs are flying around, and then at the end they pull everything in real tight, spin fast, and then throw their arms up. When they do that, they stop. The reason why they do that, and you see, is that their speed is increasing and decreasing based on how far apart their mass is. When their arms are very, very spread out, their mass is spread out over a larger distance than when they pull their body in really, really, really tight. Finally, Kepler's last law, the third law, can be a kind of a beast mathematically, but it's pretty easy to figure out intuitively. So mathematically, the wordage is the square of a planet's sidereal period in years is proportional to the cube of the length of the orbit's semi-major axis. That's a mouthful. So period, in that language, basically describes how long it takes the planet to make one orbit. The semi-major axis, remember, is the average distance. So, what we're really saying for this is planets that are closer to the sun take less time to orbit than planets that are further away. The mathematical relationship got tweaked a little bit by Newton, but for now, that's all we care about. So when we look at the planets, this should make sense. Mercury's orbit is much, much, much shorter than Neptune's orbit. Mercury is much closer. It orbits in 88 days. Neptune takes 164 years. So that difference has to do with their distance. So why is this the case? Well, that should be pretty intuitive to you as well. Greater distances, in other words, wider orbits, are going to take longer to travel. Additionally, when you're further away, there's less gravity, which means that remember, force equals mass times acceleration. Lower gravity means lower force, so you're going to be slowing down. Let's take a minute and review Kepler's third law. Finally, it's important to note out, I've been mostly talking about planets and the sun, but this applies to anything that does orbits. So our moon orbiting Earth, another moon like one of Jupiter's moons orbiting Jupiter, an exoplanet orbiting a different star, or even a man-made satellite orbiting Earth. All right, let's talk about why we care about this stuff. So it's nice just to study astronomy, but we can do a lot of stuff with this information too. So number one, it explains why we have tides. If we understand gravity, we know why there's a larger force of gravity when the moon is close and when they're pulling in the same direction. It also gives us clues about the gravity in stars and planets. Remember that as planets form and as stars form, gravity is heavily involved, and as things contract, it increases the gravity, and we understand that now with Newton's explanation of gravity. It also helps us find objects. So for most of human history, we only knew about Mercury, Venus, Earth, Mars, Jupiter, and Saturn, because that's what we can see. Uranus and Neptune weren't discovered until we had better technology. So Uranus was discovered by accident with a telescope. And once we looked at Uranus, we saw, hey, Uranus isn't moving the way that we think it should. So there must be something else pulling on Uranus, and sure enough, they calculated it and found Neptune exactly where the calculations suggested that it would be, just like 1 degree off. It also helps us, right now we're looking at planet X. That's the idea that outside of Pluto's orbit and some of the inner Kuiper Belt objects, that there might be a large object, perhaps the size of Uranus, out in the middle of the Kuiper Belt. And that math is basically coming from the same thing that we figured Neptune out with, and that's calculating the orbits based on Kepler and Newton's work. Additionally, when we look at other solar systems, other places we're looking for where life could possibly exist, we basically use Kepler's third law to figure out how far planets are from the thing they're orbiting, their sun, and that helps us determine whether, if it's a planet, how far that planet is and whether or not it's in that zone where water can exist, or the habitable zone. Additionally, we can use this information to predict where celestial objects will be at a certain time, and so consequently that helps us send probes places. We can, in 2007, we launched a probe that just got to Jupiter in 2015, and that's because we could send it on trajectories and we could use the gravity from planets to move it forward, and that's all possible because of our understanding of Newton, Kepler, and Brahe. Additionally, we can launch objects into space because we understand this. Without understanding this, launching something into space would be very difficult. And probably most important to your lives is that without this understanding, the satellites that we have that's powering our internet and our GPS and our radios wouldn't be possible. We have hundreds and possibly thousands of man-made satellites up there, and they'd all crash into each other and wouldn't stay orbiting the Earth unless we understood this material. Our last part of the discussion regarding orbital motion has to do with a little bit of a clarification. We've been talking about one object orbiting another, and that's not really what happens. So what happens is the two objects orbit around the center of mass. Where that center of mass is, though, varies greatly with the size of the two objects. We can see that really easy by looking at balancing an object. I have here two pencils. Both pencils start off at being fairly evenly weighted at either side. The eraser is going to be a little heavier, but otherwise they're fairly evenly weighted. If I try to balance the regular eraser that doesn't have anything on it, I'm going to need to put it pretty close to the center of the pencil. And that's because the center of gravity is basically right between the two. That would be like two objects that are relatively close in mass, like two stars that orbit each other. Both stars are going to orbit like this, orbit around each other. Conversely, if I have an object such as this pencil with a whole bunch of weight on one side from the rubber bands, when I try to balance that on my finger, I'm going to have to put my finger very close to where that weight is because there's a lot of mass over here. And so when it orbits, it's going to orbit around the center of mass. And although this side will be moving a little bit, it's the pointy side that's going to be doing all of the major movement. And so that would be like Earth and the Moon, where the Moon is orbiting around Earth, but as it does, Earth is making tiny motions. We see that even more the case with Pluto and its moon. Pluto's moon is about half of its size, and so Charon, the moon, is doing this, but Pluto's doing this. So it's kind of like a big orbit and a little orbit. If there's a humongous difference, as there is with a planet and a star, the center of mass is so close to the star, it actually lies within the star. And so that's how we get it looking much more like planets orbit the sun, because the planet's moving around a lot, and the sun is moving so little that it's just kind of doing this. It's just kind of making tiny, tiny circles, and so consequently we really don't notice it that much. You have these drawings in your diagram, and they're not remotely close to scale, but draw an arrow in and label it center of mass, and that will be the point in which they orbit. So the spots on the top will orbit each other. The ones in the middle will, the object on the left will orbit the object on the right, but the object on the right will move too. And on the bottom one, the smaller object is going to appear to completely orbit the larger, even though in reality the larger orbit is going to be doing this. Let's take one last review about the center of gravity. And that's it for our discussion on orbital motion. As always, come see me if you have any questions.